Hi there. Well, welcome back. Today we're going to continue our talking about related rates. We talked about area before, so today we're going to talk about volume. So these are the 7 questions that we would address today for part of our notes. I'm not going to do them all. I'll start some. The worked out answers will be on Google Classroom for you to have a look at. So everything we talked about before in terms of how things change with respect to time will still apply. But now we need to know formulas for volume instead of formulas for area. So first question here is water is being poured into a cylindrical tank whose radius is 10 feet. Time is going to be recorded in seconds. So compare the rate of increase in volume of water with the rate of increase in height of water in the tank. So they're not giving you any real specifics, they're just looking for an expression of what you would have if you completed this comparison. So diagrams are definitely helpful. So I have my cylinder. What do I know about cylinders is they have a radius and they have a height. So what am I told here? The radius is 10 feet. And what's happening is water is being poured in here. So maybe it started with a very low level, and then as time goes by, the level of water gets higher. So is there something here that's fixed? Because we've seen before, if you have a fixed value that doesn't ever change, that needs to be thrown into the formula for whatever you're talking about right away. So what am I talking about? I'm talking about volume of a cylinder. So the formula is pi r squared height. If something here is never changing, I need to throw it in right away. That is never changing. So this needs to come in before I differentiate. That needs to be put into this formula. So I now have, putting a 10 squared in here, I will have 100 pi h. So a minute ago, it kind of looked like I might have an issue because I'm not allowed to have 2 variables on the right-hand side of my equation. I don't have 2 variables now anymore. So I'm good to go. I can differentiate with respect to time. So that would be dv over dt is, there's my numerical value, 100 pi times 1, but I need to follow that by dh over dt. So how many unknowns are here? Oops, sorry, that's not an unknown. I have 2 unknowns. So somebody either needs to give me how volume is changing, then I could figure out how height is changing, or if they gave me how height is changing, I could figure out how volume is changing. But this is all I was asked to find, is just a comparison equation relating change of volume to change of height. So I'd be done. That's it. Part 2, or the next question here, is more specific. It says we do have a cylindrical tank. It's being filled at a certain rate. So this idea of liters, that's a volume or capacity quantity. So I need to do some changing there before I continue, but it's being filled. So the volume is increasing. Determine the rate of change of the height of the liquid if the radius of the tank is 50 centimeters. So again, I would start with a diagram. So my diagram, I have a cylindrical tank. The radius is 5. And this is being filled. So again, this value is changing. But the radius is never going to be changing. So this was a question about volume. They told me that dV over dt, how the volume is changing, it's increasing by 12 liters per minute. That liter is a capacity measurement. It doesn't help me when I'm talking about this being 5 centimeters and looking for a height. So I need a connection between liters and centimeters. So knowing that liters is the same, or not the same, but if I have 12 liters, I can say I have 12,000 milliliters because there's 1,000 milliliters per liter. I have that connection. And then another wonderful connection is that knowing every time I have a milliliter, that is 1 cubic centimeter. So I can change this one more step down to a linear measurement that this many milliliters is 12,000 cubic centimeters. So now I've changed this rate of volume changing with respect to time into a linear measurement. That is great because the radius was given to me in a linear measurement. So what is my formula for volume? Because this is all about volume. Pi r squared height. Is there anything fixed about the water in this tank? Yes, that 5 can go in here right away. Putting a 5 in for radius and squaring it will give me 25. So I have 25 pi h. So that is now forever the formula for this. If I want to differentiate it now, I have dv over dt is 25 pi. Derivative of h is a 1 followed by dh over dt. So this is an unknown, this is an unknown. I'm being asked to find how is this height changing according to what they gave me for this information. They told me that this volume was changing at this rate. So I can put in that information for here. So I will have this 12,000 is 25 pi dh over dt. I will take this, I will divide, I will reduce. Typically you will keep your answers in terms of pi. So you would not go to a decimal answer unless you were asked to go to a decimal answer. I'm just going to look here so I can give you an exact value. When I'm done reducing after I move this here, I will have 25 over 5 pi. So that is my dh over dt. But units are very important. What would height have been measured in? That came down to centimeters. What is time measured in? That came down to minutes. So you simply carry through the units you would have had here. So I have the height increasing at 24 over 5 pi centimeters per minute. So that would answer that question. Okay. The next one on our sheet we had, is I have a balloon. So picture what a balloon looks like. It's a sphere. It's being filled with water. So what's happening as you're doing that to the balloon? All sorts of things are changing. The radius, the diameter are changing, the circumference is changing, the surface area is changing, the volume is changing. But what are they asking you about? They want how is the surface area changing when the diameter is 10. So you would need to know what is the formula for surface area of a sphere so you could tackle this question. So we will give you these formulas, but you should know them. There's no point in not knowing them. So for a sphere, surface area is 4 pi r squared. That's good to go. I have one variable right here. Would something not be changing about a balloon as you're blowing it up? No, everything about it is changing. So there's no fixed values to throw in here. So how is surface area changing with time? Well, I have a 4 pi, but I'm going to add a 2 to it. So I have 8 pi r. And how is r changing? That's my dr over dt. So unknown, unknown, unknown. So I have three unknowns here. I better know 2 of them to proceed with my being able to answer my question. So the radius is changing. So there's my dr over dt. How is the surface area changing when the diameter is 10? Well, if the diameter is 10, I know the radius is 5. So they've given me 2 pieces of information that I can fill in. So they're asking me to figure out how the surface area is changing. So that is the point of the question. That's what I'm looking for. When the radius is 5, they told me the radius is changing at a rate of 4 centimeters per second. So all these times together, I will have 160 pi. And what are my units? This was all in centimeters. So surface area would be centimeters squared, time would be seconds. So that's how my surface area will be changing at that time when everybody stopped the world and the radius was 5. That's exactly what was happening to the surface area of that balloon. That's how it was changing. It was increasing, because this is positive, by 160 pi cubic centimeters every second from the amount it was a second before. Okay, so that's that one. Now, what else could happen? Why do you always think you have to fill up that balloon? Maybe it's leaking air. So now they're giving me a volume because it's cubed, a rate of how volume is decreasing. So that's a dV over dt, but it's negative. At what rate will the radius be decreasing in two different scenarios? So I'm still dealing with a balloon. I'm still dealing with, this is now volume. So now we need to know volume of a balloon. That's 4/3 pi r cubed. That's only one variable right there. Is something fixed and never changing as a balloon is leaking? Nope, everything is changing. So you differentiate, you have dV over dt, bringing my 3 down, it would cancel this 3. So I will have 4 pi r squared and dr over dt. So I need how the volume is changing, I need a radius, and I need how the radius is changing, or those are the two things I'm being asked for. This question tells me the dV over dt. I'm losing this much volume, and my radius is 6. Okay, so I'm losing 25 cubic centimeters per second. And that happens when my radius are at 6. So I'm going to solve, I need a squared there. I'm going to now solve for how the radius is changing. So this whole value, so 36 times 4, that's 144. Those values will go on to this side. So I'm going to have, I said 144 pi. That is my dr over dt. So how do I answer this in a question? The radius is decreasing. So we always need to answer a word problem with a statement. I should not say the radius is decreasing by negative 25 over 144 pi, and this was centimeters. Okay, so this is centimeters per second. How come? Radius was in centimeters, time was in seconds. Don't say a double negative. Don't say I don't not like math, because then you're saying you love math, right? So a double negative will misconstrue your answer. So if you're going to put a statement here, you would say the radius is decreasing by positive 25 over 144 pi centimeters per second. And then you have properly answered that. Okay, so that's that one. Number 5, I'm going to let you have a look at that one yourself. So we're talking about pouring water into an aquarium. They give you dimensions of length times width times height, so it's a prism. So they're asking you to figure out, as time goes by, the rate of change of the height. So how is the height of the water in the tank changing as time goes by? So again, picture that thing, right? So you're going to picture this aquarium. Right? And so originally it's pretty empty. You don't have very much water in it. We have like this much water happening. Okay, but you're filling it. So as time goes by, all of a sudden we have much more water in it. What has changed about that water? Has the length of the water changed? No. Has the width of the water changed? No. Those are fixed values. Has the height of the water changed? Yes. So you need to look back at the information you're given. Whatever was fixed needs to go in right away. So length and width, the 60 and the 30 would go in right away. The height, which is your last measurement, does not go in because that's what is changing. So how do you get volume for a prism? Length times width times height. The volume or the length was 60, the width was 30, the height is changing, but now when you work this out, you have a much more simplified formula. And this is representing that tank forever and ever and ever. Now you can differentiate that with respect to time and see what you're left with. Okay. The other one I want to have a quick look at here. So number 7, I'm going to leave for you. Number 6, we have sand pouring from a conveyor belt. And as the sand is pouring, it is creating a pile of sand in the shape of a cone. Now we're told the sand is piling up at this rate. The fact that they're giving me cubic meters, I know that is a volume situation they're giving me. So they've given me dV over dt. As that is happening, at what rate is the height of the pile increasing 4 minutes after the pouring starts? So this is like a standard of excellence question. This is really going to take me doing a lot of thinking and manipulating my formula. But we know as this is going on, I am creating a larger and larger pile of sand. So there's this conveyor belt and sand is, being poured. So at the start, there's my pile of sand. A little bit later, there's my pile of sand. A little bit later and a little bit later, that pile of sand has gotten larger and larger. So definitely volume is increasing, height is increasing, radius is increasing. This really is a cone situation, and volume is forever increasing. So what is the formula for volume of cone? That's area of the base, so pi r squared, times the height, but we divide by 3 because it comes to a point. This is not a good situation. I cannot have two variables on this right-hand side. So I need to somehow get everything with just r's or everything with just h's. They must give you a hint, and they have. Here they said the radius is double the height. So that happens forever. So that's a fixed idea. The radius will always be double the height. Okay, so this will always be double this. The radius will always be double the height. They have given me now a substitution for r. R is actually 2h. So if I did that, okay, so let's take out r and let's put in 2h, but we have to square it. And if I work all this out, I'll get 4 pi over 3h cubed. At the end of all my simplification, I'll get that. This would be a wonderful formula if they are going to ask me something about how the height changes. Because look at how you've set this up. This is going to be dv over dt. Over here you'll have dh over dt. If they're asking you about radius, you made the wrong choice because you have no r's left here whatsoever. But they're not. They are asking you about height. So this manipulation was perfect. You now have information about h's as volume changes, so you've made the proper setup. So had they asked you for something about r instead, you would have simply isolated this h. You would have said h is r over 2. And you would have gone here and replaced all the h's with r's. So everything here would be r's. And then you'd be good to go. So now you need to differentiate this formula. So you'll have dv over dt. The 3 comes down. It's going to cancel that 3. I will have 4 pi h squared and then dh over dt. Okay, so I need how volume is changing. I need height at a certain time, and height is changing. So the question asked me, how's the height changing? So this is what I'm looking to solve for. So did they tell me how the volume is changing? Yes, it did. It said it's increasing at a 1/2 cubic meter per minute. So I know this. I can put in a half right here. And then I need to put in height, and I need to square it. So do I know the height of the pile of sand? They're saying, well, it's going to be 4 minutes after the pouring starts. This makes it tougher. So 4 minutes after the pouring starts. Think about it. Before the pouring starts, there's no sand whatsoever, right? 1 minute later, okay, if I have this as a rate of volume, a 1/2 cubic meter per minute, how much sand is there after 1 minute? Well, a 1/2 cubic meter would be there. How about after 2 minutes? Well, I times this by 2. After 3 minutes, I'll times by 3. So after 4 minutes, I'll times by 4. So a 1/2 times 4 is 2. So now I know I have 2 cubic meters of sand. So now we know the situation is me having 2 cubic meters of sand. Can I get the volume from that? Yes, you can. You went to all this work to get the formula for volume of this cone. Volume of this cone is 4/3 pi h cubed. You now know what the volume is. The volume is a 2, so that can go in here. So this becomes a 2. I need to isolate that h because that's what needs to go in here. I need a formula for h, and then I can square it. So moving the 3 up here and the 4 down here and the pi down here, I'll have 6/4 pi is h cubed. I can reduce. That's 3/2 pi is h cubed. So what's h? The cube root of all of that. So unfortunately, because it's not a nice value, that's exactly what you're taking and putting in here. So here's where you for sure need your calculator. And again, you should not be using a graphing calculator. That wasn't part of the course. You needed to be familiar with how to use just a scientific calculator. So I'm going to take this value and put it in here. So at this point, I for sure would probably want to work all this out with a calculator and save it. Okay, so I'm going to have some kind of value here. After I throw this value in, then I will go 0.5 divided by that answer. Okay, let the calculator do the tough part of the work for you, because a question like this will ask you for a decimal answer. So after you go through all that, I will give you the answer just so you know what you should get in terms of, let's see here. I'm looking for how the height is changing. I should get a value of about 0.065, and this was meters per minute. Okay, so a little bit extra for sure, but the idea is always going to be the same. You're getting a formula, you're deciding if there's something in terms of a fixed value to throw in there, otherwise you're differentiating, then you're throwing in your values at that point in time. Watching for your units is very important. So this sheet and all the worked out solutions are going to be on Google Classroom. There's also, besides your textbook questions, there's going to be a worksheet to do just so you get really good at this stuff. And that's pretty much our covering the basic ideas for related rates to this point. Okay, thanks for listening. Bye-bye.